Our journey begins with learning about vectors, which is something that will appear very frequently in many topics in physics. So the sooner we get comfortable with its concept and use, the easier our lives will become in the future. But before getting into it, let's first go back, say, some 40 millenniums ago, a world before numbers. Back then, people still had their ways of describing quantities, such as a few potatoes over here, many corns over there, or this place is close, and that place is very far away. While these methods worked, it was not precise and created lots of confusion. Once the concept of numbers was invented, quantifying things became much easier. Numbers also enabled us to add, subtract, multiply, or divide those quantities. Like numbers, vector is also a mathematical tool that helps us understand, describe, and work with certain quantities in the physical world around us more easily. Specifically, those quantities that can't be described solely by numbers. For example, if Corn wants to show Potato the way to get from A to B, he can't just tell Potato to walk 5 steps. He must also tell Potato the direction, such as 5 steps to the right. So, vector is used whenever we need to describe a quantity that has both magnitude and direction. The magnitude gives us the size of the quantity, and the direction tells us where it's pointing. To visualize our vectors, we'll be drawing them as arrows. The magnitude of a vector will be expressed by the length of the arrow, and the direction will be indicated by the arrowhead. Here is a simple example of a vector A that has a magnitude of 2 units and is pointing in the positive x direction. The first thing to know about vectors is that 2 vectors are equal if they have the same magnitude and direction. This means we can redraw another vector 2 units in the positive x direction anywhere, and it would be considered the same as our vector A. It also means we can grab our vector A and move it anywhere we want as long as we don't change the 2 qualities that define it, which, again, are its magnitude and direction. Given this advantage, we should choose to place our vectors where it's easiest for us to visualize and solve our problem. In our current case, the best place to put our vectors is at the origin, which is what we're going to do in the next few examples. To describe our vector in writing, we will first need some quick notations. As you might have noticed, vector A is represented by the letter A with a right arrow above it. Vector A is pointing toward the positive x direction. But instead of having to write that whole line of description out, there's a much better way to represent it using this I hat notation. It's called the unit vector I and is used to describe direction. The meaning of I hat is simply in the positive x direction. This short and sweet notation tells us everything we need to know about vector A, which has a magnitude of 2 units and is pointing in the positive x direction. If we just need to talk about the magnitude of vector A, we can use this notation that is similar to how we write absolute value. Like absolute value, the magnitude of a vector is always positive. So this is how we say that vector A has a magnitude of 2 units. Note that in this case, we don't have any specific unit for our coordinate system. If we did, and if that unit was meter, for example, we would say that the magnitude of vector A is 2 meters. Using this convention, we can express this new vector B as -3 units I hat. This notation tells us that vector B has a magnitude of 3 units and it's pointing in the negative x direction. As mentioned earlier, the magnitude of a vector is always positive, so this minus sign actually belongs to the I hat and its job is to tell us that the vector is pointing in the negative x direction. The minus sign can be placed in front of the I hat to emphasize this fact. However, you will often see it come at the front of the notation because it looks cleaner this way. Here is vector C that has a magnitude of 4 units in the positive y direction. The unit vector for the y-axis is j hat, which is the equivalent of in the positive y direction. So here's how we can express vector C. Some of you may have been introduced to vectors before in some other math classes and may be more familiar with how vectors were expressed using ordered pair. For example, vector A is 2, 0, B is negative 3, 0, and C is 0, 4. If you are more comfortable with writing vectors that way, it's not a bad practice to write down that ordered pair first and then use it as a guide to generate the unit vector notation. After having vector A as 2, 0, we can easily rewrite it as A equals 2i plus 0j. Similarly, from negative 3, 0, we can generate B equals negative 3i plus 0j, and from 0, 4, we can get C equals 0i plus 4j. Now let's look at this vector D. From the picture, we can see that to draw vector D, we need to go 5 steps along the x-axis in the positive direction, and then 4 steps along the y-axis in the negative direction. Therefore, the ordered pair that describes our vector D is 5, negative 4, and the unit vector format for vector D is D equals 5i minus 4j. What this notation tells us is that vector D is made up of 2 vector components: a horizontal component with a magnitude of 5 units in the positive x direction, and a vertical component with a magnitude of 4 units in the negative y direction. We can also write them separately as dx equals 5i, dy equals negative 4j. To solve physics problems, it's very useful to develop a habit of expressing every vector in this unit vector components format. We will see why it is so in the next video. Unfortunately, when a problem gives us a vector, it is often in a different form. So let's look at an example and see what we should do in that case. Let's say the problem gives us vector E that has a magnitude of 6 units and is 37 degrees above the negative x-axis, and we are asked to express E in its vector components format. The first step is to visualize vector E in a sketch. Starting with the axis mentioned in the question, which in this case is the negative x-axis, we were told that E is 37 degrees above it, which is about this much. Since vector E is the only object in our drawing, it's up to us to decide how much is 6 units. The best practice is to always make sure that our drawing is of a decent size, because we will be using it to solve our problem later. In order to express E in its vector components format, we will need to know the magnitude and direction of this vector EX over here and EY over here. Just by looking at our drawing, we can easily see that EX is in the negative x direction, which we can express as negative I, and EY is in the positive y direction, or j. To find their magnitude, we'll be using this right triangle. Let's call the length of the hypotenuse E, the length of this side EX, the length of this side EY, and this angle alpha. We already know that E is equal to 6 units, and alpha is equal to 37 degrees. Now we can find the two sides of this right triangle using the SOHCAHTOA trigonometry functions. SO means the sine of angle alpha is equal to the opposite side divided by the hypotenuse. From our picture, we can see that the side that's opposite to the angle alpha is EY, so sine alpha is equal to EY over E. Rearranging this equation gives us EY equals E sine alpha. Ka means the cosine of alpha is equal to the adjacent side divided by the hypotenuse. The side adjacent to alpha is EX, so we have cosine alpha equals EX over E, or EX equals E cosine alpha. Since we already have the values for E and alpha, we can use our calculator to solve these two equations and get EX equals 4.8 units and EY equals 3.6 units. Now that we have the magnitudes of the two vector components, we can just plug them in right here, which gives us vector EX equals negative 4.8i units and vector EY equals 3.6j units. We can either leave it like that or write vector E equals negative 4.8i plus 3.6j units. Again, this expression tells us that vector E is made up of two vector components: a horizontal component, which has a magnitude of 4.8 units in the negative x direction, and a vertical component, which has a magnitude of 3.6 units in the positive y direction. Although we didn't need to use TOA to find EX and EY, we can still make use of it to verify our calculations. TOA means the tangent of angle alpha is equal to the opposite side divided by the adjacent side. So, tan alpha would be equal to EY over EX, or 3.6 over 4.8. Therefore, alpha equals arctan 3.6 over 4.8. Plugging this into our calculator gives us the value alpha of 37 degrees, which is what we expect, so we know that our calculations were correct. There is another way to double-check our work using the Pythagorean theorem, which states that the square of the hypotenuse is equal to the sum of the square of the other two sides in a right triangle. So we have e squared equals ex squared plus ey squared. Therefore, e would be equal to the square root of ex squared plus ey squared. Plugging in the numbers gives us e equals 6 units, which is also what we expect. To wrap this video up, I just want to reiterate the importance of expressing any vectors given to us in either one of these vector components formats. In the last example, we learned how it can be done by drawing a simple sketch and then applying some basic trigonometry functions to solve for the two sides of a right triangle. Please review this as many times as you need to and do as many practice problems as you can, because this is a process that we will be using for hundreds of times in the future.